Oh, it isn't. Thank you. Good afternoon, everyone. Today I will present our joint work done with my colleagues from the University of Latvia, Olga Grigorenko and Dmitry Gromov. Also, some of our students are involved in the research, and some of them participate at FSTA also. For example, Martin Zemlitis is one of them. I will start with a short motivation part. And I hope in such a way to reduce standard questions about applications, because my talk is devoted to the project, so-called application-oriented project. The title is a fuzzy logic-based approach to the value of information estimation in optimal control problems under uncertainty with applications to ecological management. And in our proposal, we announced two application areas for our results. The first one is pollution control, and the second one deals with renewable resource using of renewable resource. And our main aim is to extend the theory of value of information to the case of expert-based information. And in our opinion, fuzzy framework, fuzzy approach is very good technique to do this extension. So we developed the theory of value of information in the framework of a fuzzy logic-based model. I continue with a description of the main concept of this talk, the concept of value of information. And of course, information has an economic value because using new information gives possibility for decision makers to make better decisions than they could make without this new information. The notion of value of information initially was introduced in the late 60s. You can see two main papers published in 1965 and 1966 by Stratanovich and Howard. And of course, one can consider also a modern presentation of the theory in several books. Some of them are shown on the slide. Two books published by Springer. And the theory of value of information lies on the intersection of such theories as information theory, decision theory, and optimal control theory. Of course, there are many papers devoted to applications of the theory of value of information published during the last 10 or 15 years. I show on my slides two papers. The first one is published in 2024, the second in 2025, and both of them are devoted to ecological application. And one of the authors of both papers is Thorsten Ullmann. I want to tell that collaboration with him give us some impulse to start this project. The title of This paper is the value of information in water quality monitoring and management, and Thorsten Uckmann and his colleagues works in the standard stochastic approach, but we solve almost the same problem using fuzzy approach. It is the second paper. As I told, this theory lies in the intersection of three theories, and one of them is optimal control, and I will explain the concept of value of information. Considering optimal control problem, I use notation X for states, U for control, and J for utility function. In such notations, optimal control problem can be formulated as maximization problem of the aggregated value of utility function. And we compare the case shown on the previous slide with the case with so-called perfect information. It is the case when the decision maker can learn the realization of the state before taking a decision. And so we can use so-called optimal control of the optimal response, U star, and before aggregation values of the utility function, we change U for U star. And it is the difference between two formulas. This new formula in the case of perfect information, and this formula in the case without information. And if you take the difference between such two expressions, then we obtain the expected value of perfect information, EVPI, and it is the main value under consideration. Of course, the classical approach is stochastic approach, and in the framework of stochastical modeling, states are considered depending on a random variable denoted by Xc. And in this case, in the formula of EVPI, we use the mean values, yes, or the formula now is written in the following form. And in many papers, authors use so-called naive approach for the cases when it is not so easy to deal with the mean value of the utility function. And this naive approach is realized by considering the mean value of random variable C instead of taking the mean value of the utility function. Of course, also dynamic setup is under considering, but I haven't enough time to go in details for this case. The main questions to ask and to answer in the framework of this theory: does additional data provide additional information? What do we gain from the additional piece of information? Which information is more valuable, and so on? Of course, obtaining perfect information is in many cases is impossible, and so instead of obtaining perfect information, the decision maker deals with so-called partial information. And in the model, we consider so-called information vector H, and information service denoted here by H, by bit H. And in this case of partial information, there are aggregation on two stages. One aggregation is before maximization, and this is aggregation on the space of all states corresponding to information H. And after maximization is the second aggregation for overall information vectors from information service H. In this case, we also can speak about value of information provided by information service, considering by such a difference. And of course, the information structure plays a very important role in this context. And also some remarks about dynamic case. I will not go to the details, taking into account that we will consider states responding to information vector as fuzzy sets. We use aggregation instead of integration, and we consider maximization in the fuzzy sense. So we rewrite formula in such a way, and the main focus for our research is comparison of two information services, H1 and H2, and we consider the case when the information service H2 differs from H1 due to additional information considering in the framework of H2. So we consider the value of this additional information as the difference between two expressions, one obtained by using H2, and the second obtained by using H1. This is our proportion and our plan. Of course, the classical approach is developed in the statistical statement, and this classical approach has its drawbacks. In many situations, probability doesn't exist due to the nature of the problem, due to the nature of data. And in this case, fuzzy logic-based model is more appropriate. And of course, this young approach allows us to involve in the model also expert-based information, and it is our main merit. If I need to characterize the current state of the art, papers devoted to applications mainly work with realistic setups, with estimations for profits, expenses, and so on. Only few states are considered, and authors use frequency-based estimations for probabilities. This is main aspects of recent published papers. Now, one of them mentioned on the fifth or sixth slide is the paper devoted to the value of information in water quality monitoring and management. Yeah, deals only with two values of control, and only with two states, bad state and good state, but it is with concrete economical interpretation, because the payout function is defined on the basis of two parameters. N is the cost of non-reaching good ecological status, and C is the value which equals to cost for management of pollution in this region. And as it was shown, the result on the previous slide that the value of information is evaluated as 9, I don't remember, million euros or so on. Our first problem under consideration also is connected with evaluation of water quality, and we use not probability distribution. In our case, the structure of the data is such that membership function is used. We use fuzzy sets. We need to find appropriate optimization technique and aggregation technique to work with fuzzy values. Our data about Latvian rivers come from Latvian Environment and Geology Center. They published overviews, and this overviews about every river under consideration contain information given in such form, 5 measurements, 5 characteristics, and also the table given by experts, which characterize the quality of water, very good, middle, bad, very bad, dependently on the measurements. And I want to refer to the talk given 2 days ago on Tuesday by Martin Zemlitis, which consider expert-based, fuzzy rule-based system to obtain function me for such a situation. Yes, membership functions are built on the base of this table obtained from the overview. Yes, and as I already told, the report given by Martin Zemlitis, it is also the part of our research. He built an implicative fuzzy rule system for river water quality assessment based on expert opinion. So as a result, we can obtain such membership function by which we can characterize water quality. And in the case when we take the diversified value by applying one of diversification methods, then we already can realize so-called naive approach. Yes, but our merit is to continue work with membership functions. So if very simple example will be taken, yeah, then in the case of membership function given on the previous slide, we obtain fuzzy values for the payoff function shown for both case of control parameter u equals to null and to 0 and u equals to 1. So now it is very important to decide in which stage of evaluation diversification will be done. if we defuzify all the values and then solve the optimization problem with respect to U, in this case, we realize the naive approach, yeah, and it will be done very easy, but it isn't the way we want to go, and we can start with maximization of the utility of the payoff function, and then defuzify result on the next stage, or maybe on the stage after aggregation. It is the question we think about now. So for conclusion, first of all, the model take into account the structure of data. Values based on data are considered in the form that give us possibility to apply fuzzy rules based on expert opinion, and after that, for analysis of payoff values, we realize different schemes, and two ways are possible. The first one, if diversification is made before maximization, and the second one, when diversification is made after. And of course, we are interested to work out combined information systems, including also statistical data, if such statistical data are available. Yeah. Dynamic setup is our next merit, but we are very far from this last topic. From me, this is.
Thank you. Thank you. Short question. Long question. Should we change it out because I'm also one of the authors. So thank you again. And we move to the second talk. Which is going to be performed by Isina Petkindeva from funding partition to reproducing kernel. I hear this place in
Okay, very good. Okay, so yeah, good afternoon to everybody. This is my pleasure to be here and discuss with you. I cannot say that the last results, because I was working on this topic for, say, last 2 or 3 years, and step by step I tried to discuss with you on different conferences. So in my opinion, that right now, I more or less prepared the theoretical background, and I will discuss today this background, and then we will see how we can proceed. I mean, because this is very wide field to work together. Okay, so what the main topic or the main focus of this presentation? The main focus globally is to contribute to the theory of machine learning, actually, because now we are asked to work on the so-called interpretability of AI systems. And of course, we understand according to our background, according to our knowledge. And so I will just present what I think can help in this direction. And we will discuss today the so-called kernel methods in machine learning, and especially the terminology which probably everybody takes as it is without full understanding what does it mean. I mean, only intuitionally, but working with the so-called feature space, because we know that when neural network is applying to any kind of problem, so the first step which it does in general, it tries to extract features from the available data. And what are features? This is for me, at least at the beginning, was the word which I couldn't understand. What actually is extracted? And so step by step, I, according to my level of understanding, I understood what does it mean, and I would like to share with you this knowledge. Okay, so here you see that we will be focused on the so-called kernel method in machine learning, and kernel. So so this talk, I'm sorry, is more theoretical, but I will try to explain semantically every theoretical expression. Okay, so this is kernel method in binary classification. Just to show you how it works, because so everybody has intuition how, for example, a linear regression works, and where is kernel, how we can raise up from linear regression to the kernel regression. So here is a partial answer. The information is given in the form of the set of training samples, and the kernel method actually remembers each pair, each input pair, trying to remember. I will explain details later. However, we now take it semantically. Tries to remember every ith training example and learns for it the corresponding weight. Okay, so if we take it as it is, then the binary classification, so assume that we did everything which is assumed, then prediction for an unlabeled input x prime is performing by computation this the result of this expression when we substitute all data here. And after that, we will obtain the corresponding value y hat in such that, because this is a sine function, so this means that it produces two values, either -1 or 1. If -1, then classification is done with respect to one class, and the opposite class if we have 1. So this is the main approach, and just terminology is such that we are trying to characterize binary classification using a kernel method, working with so-called regressors. And regressors, so are represented here as actually rows of this kernel, So as it is written, so every row of a kernel remembers, the input data, and then it compares. And comparison is performed by substituting the given data into this kernel function, So the idea that is connected, is as follows. We use, so the most important is how comparison is done. We used to estimate the result of comparison, for example, computing the inner product, right? However, this inner product, this is particular case because it depends on the space. And the general understanding how the inner product can be replaced is just this kernel approach, So this means that this kernel stands for somehow generalization of any inner product which we can put instead. Okay, so but we will be focused on the regression. Regression means that, again, given data, we shall find some separating line, if we think after that about classification. However, this regression line is the main idea or the main goal of the problem which we will be considered. Now, the most important here is this theoretical result, which is due to the German guy whose name is Scholkopf. For me, it's difficult to pronounce. And this theorem, this is very important. I will try to explain the details. So what is given? Assume that kernel is given, and this is positive definite kernel. I will explain later what does it mean. However, now we have a kernel defined on a non-empty set, and this kernel determines, again, later will be discussed, corresponding kernel Hilbert space. So K here indicates that it is connected with the kernel. So this is the initialization. Then the input data is a training sample as a set of pairs, input and outputs. Then also we require any strictly increasing real valued function, which will help to make a penalty on increasing norm. Yeah, so it's any function. And again, any so-called error function that somehow estimates the difference between what we want and what we have. Then, so this error function determines the so-called empirical risk. And the result is fascinating. Yeah, look, so the result says that any minimizer is the function f, which we put here. Yeah, so any minimizer of the empirical risk that is represented in this form here, as I said, this is the how we estimate the difference between what we have and what we what we have and what was given. So this is empirical risk plus this penalty term that somehow suppresses the growth of the norm of this function. So this answer to this minimization admits a representation of this form. So this is linear combination, as you see, of the kernel nodes. Yeah. So this is the role of the kernel. Yeah. As you remember, the kernel, we started claiming that we have it at disposal. Yeah. And now, but risk is arbitrary. Yeah. So this is very important. So this means that we are able, or the answer is represented as a linear combination, yeah, of known actual rows of this kernel. However, these weights are what to be found. And actually, you know, so neural network, yeah, after learning, yeah, also is focused on finding weights that somehow contributes, yeah, to computation of this form. Okay. So this expression tells us that if we set up all parameters, which I explained, then we can find the solution to the regression problem using this form. That's great. And what is left is to explain the meaning of all input parameters, yeah, to this theorem. So step by step, what is reproducing kernel Hilbert space? We shall leave there. Yeah, because the norm, yeah, is taken from this space. So we shall understand how we can construct this space. Okay, so the definition actually is a bit far from the problem. So if we have a set and we have a Hilbert space of functions on this set, Hilbert space, I will recall, so this is complete linear space with inner product. So this is the notation of the inner product. Then we assume that actually this is definition. Yeah, this space is reproducing kernel Hilbert space. However, kernel is not here. Yeah, if the evaluation functionals are continuous. So evaluation functionals, what are they? So they take function and with each x is element of our set. So it brings the value of function at the point x. So we have as many functionals, as many elements we have in our set. And actually, yeah, this means that this is like a column, yeah, and for any function, this functional picks up the value of this function at x. Yeah, so this is functional, means function is input and real value is output, and it should be continuous. This means that our space should be rich in a certain sense that at every point x from the definition set, we should have enough values such that the range of these values in a certain sense rich enough, continuous. If it is, then this space is called reproducing kernel. However, kernel, as I said, is not there. Now, what are reproducing kernels? In this setting, we start from some Hilbert space H, and we have a kernel as a function of two variables. And then we say that if this property is fulfilled, this means that the kernel, using the inner product of the Hilbert space, helps reproducing the value of the function at any point. So at this moment, take it as it is formulated, because I am not able yet to explain, but more or less semantical is seen here from this definition. And what is important, and the previous two notions, reproducing kernel Hilbert space and this reproducing kernel, are connected using this theorem. Means that if we have a kernel that fulfills this property, then there exists one Hilbert space such that that kernel is reproducing for this space, and vice versa. Every kernel, every reproducing kernel has corresponding uniquely determined Hilbert space. However, the proof is a kind of existential, and it's not possible, because this is a convergence proof. It's not possible to extract the construction, and therefore we will consider some sufficient conditions how we can put these things together. For this, we need the notion of positive definiteness. It's given here. It relates to a kernel. So kernel is positive definite if it is given by a symmetric function on a certain space, and it fulfills this property. However, again, to analyze this property, and so if you have a kernel, and especially if kernel is defined on the infinite space, it's not possible to estimate the validity of this property, and therefore we need some sufficient conditions. And so they are, luckily they are, and now we see the terminology of a feature map, which I am happy to explain here. So what it is? So if we have a set, like a set of objects, and if we have a Hilbert space on this set, means set of functions, then feature map is any map such that it connects any object from X with some function from this Hilbert space. No information how, just a map. So this only uniqueness, is working here. So for every element, we just find the corresponding function from the Hilbert space, and this map we call feature map. Okay, so what is important for us? And F as a source of images, is called feature space. What is important is every feature map defines a unique positive definite kernel on X, and this is very simple. So this means that if we take this result as a possible way how determine positive definite kernel, so it's here, and so when we have kernel, we are happy, and then I will explain how our life will be simpler if we have this problem. Okay, so when we state that, just here previous, so we have this kernel. The next step is how we can develop the corresponding Hilbert space, means space of functions. So now we shall determine functions. However, this way of determining is not that obvious, in a certain sense. Okay, but in any case, it gives us some idea. Let us discuss. So we have Hilbert space, we have a feature map, everything, and now we consider the linear space of functions that are determined in this way. So look, first of all, we have space, we have inner product in this space. And then we take functions such that for, so function belongs to this space if there exists another function from F such that this function which we would like to have in our space is the result of this inner product for every X. Yeah. So it's a bit, so it's a bit unintuitive, yeah, because the definition again, yeah, uses the existence. Yeah. However, nothing better exists, yeah, unfortunately, unless we will reach the end of my presentation. Okay, and if so, this definition, mathematical definition, yeah, it defines theoretically the set of functions. And in order to have Hilbert space on this function, we define only norm. I will not again tell you how inner product on this new space H5 is defined, because it is again a convergent process. However, the norm can be defined here. Therefore, this space is a Hilbert space, and moreover, this is Hilbert space that is reproducing kernel Hilbert space, where kernel will be determined, yeah, using this feature map. Now we put all things together with which we spoke about before. What is important here? Yeah, the kernel. Yeah, what is important here is that this space has another inner product than the inner product which was taken from the original space. So this is, interplay between two inner products. And now the last part of this presentation is how we can connect this highly theoretical background with what we know very well, with the notion of fuzzy partition. So my goal is that to use fuzzy partition as a source of the kernel, and then use the kernel to construct the corresponding feature map and Hilbert space. So step by step. I will be very quick here, because the notion of fuzzy partition from many presentations which I gave, and also which you listened during this conference. So what is important? Partition is just a collection of fuzzy sets on a certain universe that fulfill certain problems. So this is our favorite triangular shaped fuzzy partition. We can use it. It is uniform if these properties are fulfilled, or in other words, if there exists the so-called generating function. Generating function has this form. It can be translated and scaled in order to have all partition elements. And so this is the illustration. So we start from this generating function, and then we translate over X, just shifting it to the right, and rescale using the H parameter. Okay, what is important again for us is that we have a uniform partition. We can construct, so this is a particular case for triangular generating function. However, with the help of this generating function, we can construct a fuzzy partition kernel. So this is the generating function. We put this expression inside such that when we fix one variable, for example, the first one, it is symmetrical, doesn't matter. So then we have one basic function, one element of our fuzzy partition. So this means for us that we start partition is uniform, it has generating function gives us immediately the kernel. Okay, so we are happy we have kernel, and now we can, from this kernel, we can construct the representing, in a certain sense, kernel, using the theory which we discussed before. So step by step. So first we have Hilbert space, generating function, kernel that represents fuzzy partition. Then this is any row of the kernel which is our partition element, actually. And then if we construct feature map, just mapping any element from our universe to function, actually to basic function or to function that corresponds to a partition element, we have a feature map. When we have a feature map, we can construct another kernel using this inner product, yeah, in this space we selected at the beginning, and this kernel fulfills all necessary properties to representing kernel Hilbert space. So as we discussed above. So we have what we wanted to have, and as another characterization, as I said, yeah, so which is another characterization of functions that constitute this Hilbert space. Sorry, jumps. Oh. Yeah. Yeah, luckily for us, we can have representation in the exact form of functions from the this representing kernel Hilbert space. And these functions have this form, as you see, linear but infinite linear combination of kernel functions. Therefore, we can substitute this information to our regression theorem, which we started at the beginning, and then we can say that the solution to the regression problem, which we started from, can be found as a linear combination, yeah, of kernel functions. In this case, this combination is finite, and it is determined by the inputs of pairs which we have at the beginning. So what for us is important is that if, as I said, yeah, if we select all necessary parameters from fuzzy partition, then we can say that regression problem can be solved in terms of these functions, and these functions are nothing else as the functions represented using the inverse fuzzy transform formulas. Yeah, so this means that working with inverse fuzzy transform formulas, we can be sure that we are able to solve regression formula, regression problem correctly. So that's it. What is important here, you know, so it looks that, wow, yeah, result. However, this result was proved under the assumption that everything is estimated in a special Hilbert space, which can be constructed following all these steps, yeah, and even the estimation. So we have optimal solution. However, this solution is optimal in the space, which is somehow connected, yeah, with the way of how the problem is solved. However, this is normal, you know, so this is nothing special. This is no trick, yeah. This is only explanation how theory actually corresponds to the things which otherwise neural network computes for us, and we do not know why this result is optimal or how we can take this result. So I only wanted to say that optimality is not obvious. It is connected with the way of solving the problem. Yeah, and the step by step, the explanation is here. So thank you.
Thank you. Since we have only 3 talks, that's why we have really time for questions.
Oh, thank you.
Thank you for recalling the nice piece of functional analysis. I have 2 questions. Firstly, no assumptions of smoothness are required. Just it might be triangles or something like that. Yeah.
Yeah.
Okay. But the second question, actually, what you suggested as a statistic.
Excuse me. Yeah. One exception, because our original space, you remember, L2 means integrability.
Yeah, I know. But
yeah, that's
but the main question is as follows: your regression model is actually logistic regression.
Yes.
Yeah. So, is there really a difference between what you obtain and we in the classical logistic regression?
so this is a matter, of choice, actually, What I wanted to say is that if you prefer to work, with what you know actually, how it works, then you can create, the whole framework, according to your system of of these functions, which you love, For example, I love triangular functions because I know how they work, and therefore I can create the framework, where this solution is optimal, and and optimality, as you remember, can be proved with respect to any error function. So this is important. So this means that you can play with parameters, but playing with parameters and with the functions from your lovely space, you can reach optimality and you will be happy.
So, I mean, whether it is true, but if I consider classical logistic regression, you can go in different way and show which are Hilbert spaces and kernels,
Yes, exactly. That's the point.
Okay, thank you.
Some more questions? Maybe I ask one very short. When I saw the name of the topic, I thought that you are going to say us that kernel trick is something similar to transformations. And I mean the procedure when you use a partition, not only for regression, but in general. Are you going also in general to say us that the kernel trick represents the F transforms?
No, not at all.
That
It's only one way, so because only one way, because so we start from partition. Partition gives us one kernel, but this is not the kernel which is used there. From that kernel, we extract feature maps, and feature maps determine another kernel, and that another kernel is just reproducing.
Thank
That's
you.
the feature.
Thank you again. And the third talk is online.
Thank you.
Mihailovich Bilyana with inner inverses and solution of interval linear systems. Please, Bilyana.
Good afternoon. Greetings from Novi Sad to everyone. Today I will share with you some of my thoughts and directions in solving complex interval linear systems. More introduce the general inverse, this denotes under the name pseudo-inverse, and it is rediscovered by Penrose 35 years later. The inner inverse is a generalized inverse which satisfies the first Penrose's equation. 60 years ago, and another mathematical scientist with the same last name, Moore, established the foundation of interval analysis and interval arithmetics. It is known that solving interval linear systems with interval left-hand side vector and interval coefficient matrix is NP hard. My colleagues and I obtained some results related to maximal inner estimates of interval linear systems with a precise coefficient matrix, which is a real matrix. And I will present some of these results. Fuzzy challenges and temptations on CC in last September, and we received these 2 plates of black and white grapes, and I was wondering, is this with some purpose or it is a coincidence? So when we think about fuzzy linear systems, of Friedman type, we can say that there are many papers dealing with different methods of solving fuzzy linear systems of Friedman type. I prefer the approach of Alejandro and Gambari, proposed 40 years ago, and it is related to interval analysis. That approach was generalized by Vera Miller-Jerkovic in her PhD thesis, and Gambari recently proposed some methods for solving complex interval linear systems and rectangular fuzzy complex linear systems. So, since those two papers, it is considered square linear systems, interval, complex interval, or fuzzy complex interval, it is natural to think about the general solution of complex interval linear system and fuzzy complex linear system of arbitrary size. So with complex coefficient matrix, and on the right hand side of equation we have a complex interval vector, or on it has the vector of complex intervals or fuzzy complex numbers. So it is not my intention to disturb or interrupt anyone of the author mentioned. It is my intention to be relaxed, to be in harmony inside and outside. Here we have one example. It is the using united and tolerable set of solutions of interval linear system as it is proposed in book, for example, of Sergei Shary. When the coefficient matrix is precise, it has real matrix and it is invertible, we obtain inner estimate of united solution set. As we can see, it is unique, and also it is the maximal inner estimate as it is proposed by Kupriyanova, for example, 30 years ago, and also in book of Sergei Shary we can find some results on maximal inner estimations. When dealing with interval linear systems, we are wondering, is there formal, so-called formal solutions or algebraic solutions? And here we see exactly the unique solution, and this matrix is coefficient matrix is real and invertible. The system of four Penrose's equations for real coefficient for real matrix is the next, and it is there is a unique matrix called the Moon-Penrose inverse that satisfies for these four equations, but also for complex matrices. These four equations are the same, except that transpose is replaced with complex conjugate, transposed conjugate. And the Moore-Penrose inverse is denoted with these symbols. There are also, for example, for square singular matrices, there are some other kinds of generalized inverses. For example, the Drazen inverse is uniquely determinate. a matrix from three matrix equations, 2, 5, and 6. Then the group inverse is also uniquely determined from equations 1, 2, and 5. The core inverse also uniquely determined from 3 equations. And Drasin inverse is not one inverse in general. It is one inverse when index of matrix is 1, and it is exactly the group in inverse. We are interested in equation solving group generalized inverses, and equation solving generalized inverses or inner inverses are such that the first Penrose's equation is satisfied. They are not in general uniquely determinate. And here we have a result about consistency of linear system of equations. So linear system of equation is consistent if and only if there exists one inverse such that this equation is satisfied, and also we can express the general solution in the form of one inverses, and this is the general form of solution of consistent linear system of equation. So intention was to generalize this result to interval linear systems, and by using classical interval arithmetic and considering only closed proper intervals with addition and scalar multiplication defined as usual, and centers of intervals and radii of intervals as usual, and equality of intervals. We consider the interval linear system, but with precise coefficient matrix, which is a real matrix. And we are interested in its united set of solution. In the case of precise coefficient matrix, we have only one possibility. So the united set of solution is equal to the tolerable set of solution. Those definitions are from book of, for example, Sergei Shari, and these two set of solutions are the same, and the controllable set of solution and classical set of solution are empty in the case of interval linear system with precise coefficient matrix. And if we can see, we can take a complex coefficient matrix. We have one inverses of complex coefficient matrix, or the most famous one, the pseudo inverse. It has the Penrose inverse, and on the right hand side we can consider complex interval vector, and think about formal solutions. So formal solutions are such that components of solutions are all closed intervals. And when coefficient matrix is not completely non-singular, we can, and the system is consistent, we can obtain infinitely many such vectors, and we then can define the united inner set of solutions with all inner estimates of united set of solutions. And with my colleagues, we obtain this theorem. It is related to precise real coefficient matrix, and it can be interpreted that we have only two situations. There is no maximal inner estimates, or Each inner estimates of united set of solution is at the same time the maximal one, and this result especially regarding to result of Kupriyanova from 30 years ago, because we consider special fixed precise coefficient matrix, but it is more general since we consider arbitrary size of interval system of linear equations. We also have this theorem. It gives us necessary sufficient condition for consistency of associate interval linear system, and it is a generalization of the known result for classical interval linear systems. So we can see that all components of interval vector, it's their left and right endpoints can be obtained using the solutions of this classical system of equations. The first one is homogeneous, always solvable, and the second one is this system with and then we form all such vectors. It has all inner estimates of associated interval linear system. And maybe it is only interesting who is interested, they will read the paper. So we see that in the case of singular precise singular coefficient matrix, we obtain formal solution infinitely many. On the picture we see only two, but there are infinitely many, and their union is exactly the united set of solution, and each of inner estimates is at the same time the maximal a maximal inner estimates. Also in this example with also singular coefficient matrix, we obtained all inner estimates that are at the same time the maximal inner estimates. And here is example based on our result, our theorem, that when there is no maximal inner estimates and of united set, and finally what is the direction in solving fuzzy complex linear systems proposed 6 years ago, 5 or 6 years ago by Gambari. But only for square form of fuzzy complex linear systems, connection of inner inverses, complex numbers, and closed intervals. So we define the interval scalar multiplication of a complex interval. So we here have two classical intervals, closed intervals, and we are using standard interval arithmetic. Here is interval scalar multiplication with complex number, then addition on a complex set of complex interval is defined in such a way, like this, and when the coefficient matrix is complex and right-hand side vector is interval complex vector, we can take any one inverse, inner inverse of coefficient matrix A. And we define this is based on the result of Gambari proposed 5 years ago. So we compute W1 and W2, and that is the final result for this conference. So we have, of course, it is many conditions, but that's it, because we have complex interval linear systems, and associated complex interval linear system is consistent if and only if there exist two inner inverses of coefficient matrix A and of this matrix, such that the next conditions are satisfied. And here we see the form of general solution of associated complex interval linear system. And we see that we need to solve this one system and that one. Exactly, that is the one. That is the one system of linear equations, but the coefficient matrix is block matrix. And in their paper, Gambari, Alhviranlo, and Petritz, they used a method for solving in one example using Banashevich-Schur form. So since we have infinitely many solutions, in their example is only one solutions, I see a problematic situation. It is the complex situation, since we need first to develop methods for solving such kind of linear systems. And of course, this is a theoretical result. I think that it is important for some theoretical purposes, but in practice, we need to develop some numerical methods for obtaining solutions of such kind of interval linear systems. And so with my colleagues Maja Netović and Srđan Miličević, we sent a paper regarding generalized Banashevich-Schur form of generalized inverses, also with Đorđe Dragić and Ljubo Nedović. We published paper related to method for solving fuzzy state matrix equation that can be further generalized for with complex matrices A and B. Also with colleagues Kuzmanović, Ivičić, Ivana, and Miodragović Suzana, we sent this paper regarding complex interval T Sylvester equation that can be useful in applications, for example, considering stability analysis in dynamical systems and so on. And here we have some references. So hopefully it will be some new results with our colleague Martin Kalina related, and Mirjana Štrboja related to bipolar approaches in decision making. Thank you for your attention.
Thank you. Thank you. Questions, comments? Yes, Irina, please.
Thank you very much for the interesting talk. Your final theorem, is a kind of existential theorem, right?
Yes.
Do you have some sufficient conditions that somehow help understanding consistency of systems?
At the moment, this is bright new theorem. So for FSTA, so I will think about some maybe modified condition that will be better for understanding for readers. But at the moment, that is the only one. Also, we have that paper. We have that paper of published in applied soft computing of Gambari, but that paper, as I said, is talking about complex, fuzzy complex linear systems in the square form with a unique solution, and this is general case. So that was my intention, to obtain a general case, and of course we have many conditions here, but that's it. That's it.
Thank you. Some more questions? Thank you for coming. And
Thank you.
let's go. Thank you. Yes, thank you participants for coming. We nicely prolong our section till the coffee break. So let's come to the football match to be with our players. And thank you.